Hi all. Good morning, everyone. So let's start now. In this lecture, we will study cuts and connectivity. Like what is vertex cut, what is edge cut, what is connectivity number, what is cut vertex, what is cut edge. So basically, all these concepts we will study. Okay. So let's start. So first topic that we will study, that is what is a cut vertex. Cut vertex. So this is a vertex, or I can call it articulation point. Another concept is cut edge. Cut edge means this is a edge, or you can call it a bridge. Let's start. So what is a cut vertex? Look at this graph. Tell me, in this graph, let's assume that this graph is your network. Okay, let's assume this graph is like, I can say that these are the servers. Okay, these are the servers. This okay, these are the servers. Let's assume. Okay, all these are servers. Then tell me which server is most important. Which server is actually most important? Tell me, in this graph, which server is most important? Yes, this server B, this is most important, because remember, if you remove this, then now there is no communication. This vertex cannot communicate with this vertex. There is no communication. We cannot communicate. Okay, but you can notice that if I remove this, still this vertex and this vertex, they can still communicate. Okay, this vertex and this vertex, they can still communicate. So that is the idea. Okay, so this vertex is very important. This vertex is basically your cut vertex. This is known as cut vertex, or you can call it articulation point. Okay, this is the definition. So this vertex is very important, because if I remove this vertex, okay, let's remove this vertex. If you remove this vertex, then what will happen? Then you can notice that this graph and this graph, they are completely disconnected. They disconnected with each other. Okay, so I can say one thing, I can say that it's like in this family, this vertex is actually, okay, it is holding together. Okay, it's like this vertex is holding together this entire family. Okay, it's like okay, in a bad marriage, if there is a bad marriage, okay, some mother, father, and children, then sometimes the child is holding the marriage together. Okay, sometimes, anyway, okay, I don't know whether this is a good, okay, but I will give you a good example. So let's assume, so basically this is holding together this complete graph. Okay, this vertex is holding together. Okay, so I can say that this vertex holds this graph. Okay, so anyway, so this is the idea. Now let's see. So you can notice such vertices or edges, they hold the whole graph. Okay, so basically they have the property that they can destroy this graph, they can disconnect this graph. Okay, so this is the idea. Tell me which edge is so this is about vertex. Tell me, is there any edge in this graph? Is there any one edge? Is there any one edge which will disconnect the graph? Is there any single edge? Like single edge, for example, if I remove this, it will not disconnect the graph. If I remove this, it will not disconnect the graph. If I remove this, it will not disconnect the graph. So you can notice in this graph, there is no cut edge. We have a cut vertex, but there is no cut edge. So this vertex V, I can say this vertex V, this is cut vertex. This is cut vertex. In this graph, there is no cut edge. In this graph, there is no cut edge. There is no edge, okay, who holds this graph, I can say, whose removal will disconnect this graph. Let's see this graph. In this graph, if I remove this vertex, see, if I remove vertex 1, then this graph will disconnect. You can notice. Okay, and if I remove this vertex 3, if I remove this vertex 3, then what will happen? Then also this graph will disconnect. Okay, so you can notice this vertex 1 is also articulation point, and this vertex 3 is also articulation point. Articulation point means vertex, cut vertex. So this is the idea. Okay, articulation point, or you can call them cut vertex, both are the same things. Both are the same thing. So you can notice this vertex, if I remove, the graph will disconnect. This vertex, if I remove, the graph will disconnect. Tell me, this vertex, if I remove, will the graph disconnect? If I remove this graph, will the graph disconnect? No. So this vertex 4, this is not cut vertex. This vertex is not cut vertex. Okay, this is not an articulation point. This vertex is not an articulation point. Similarly, this vertex 2, this is also not an articulation point. Okay, this vertex 2 is also not an articulation point. This vertex 4 is also not an articulation point. And similarly, this is also not an articulation point. I can say this is also not a cut vertex. Cut vertex means articulation point. So this is also not a cut vertex. Because if you remove this vertex, okay, the graph is still connected. The family is still connected. So basically, this is the idea of cut vertex. Cut vertex is like this. Okay, if you remove this cut vertex from here, okay, if you remove this cut vertex, then the things will go. Okay, so basically the things will fall apart, I can say. Okay, yes or no? So this is your example. If you remove this cut vertex, then things will fall apart. Things will fall apart. Okay, so this is the idea of cut vertex. So what is a cut vertex? Now let me tell you one more thing. Tell me, in a disconnected graph, what will be a cut vertex? Like if I give you a graph, let's assume you have a disconnected graph. Let me give you a disconnected graph. And in the disconnected graph, let's find out. So you have a disconnected graph. Let's assume A, B, C, D, E, F, G. Tell me in this is your graph. This is your graph. In this graph, you tell me what are the articulation points. What points are the cut vertices? Which points are the cut vertices? Okay, D, F, E, G, H. Okay, so let's assume this is your graph. Now in this graph, what you do? You tell me. So what are the articulation points? Which points are the articulation points? Articulation points, or I can say cut vertices. Which points are the cut vertices? So which points are the cut vertices? Tell me in this graph. In this graph, the cut vertices are basically, see, if I remove this, then can I say, okay, if I remove this, then can I say this is this G? Can I say this vertex G is a cut vertex? Can I say this is cut vertex? This is not cut vertex. So what should be the property for disconnected graph? How to define? See, for a connected graph, you can define like this. This vertex, if I remove, the graph will disconnect. This vertex, if I remove, the graph will disconnect. So this is how you can define for connected graph. But tell me, for disconnected graph, how will you define? It is already disconnected. How will you define? What are you checking? What are you checking? Yes, number of components increase. Very good. Kusal, very good. Number of components increase. Number of components increase. So remember, in any graph, whatever graph you take, in any graph, connected or disconnected, in any undirected graph, whether it is connected or it is disconnected, okay, in any graph you take, in any undirected graph, I can say, what is a cut vertex? What is a cut vertex? Cut vertex V. Cut vertex V. Okay. Cut vertex V increases the number of components. Increases the number of components. Remember, increases the number of components. Okay. So cut vertex removal, I can say, okay, removal of cut vertex. I can say removal of cut vertex V increases the number of components. Like here you can notice, if I remove this, number of components is still 2. In this graph G, I can say what is number of components? What is number of components? That is 2. Okay, if I remove this, still it is 2. So I can say what are the cut vertices? But if I remove this, then number of components will increase. Now how many components? If I remove A, how many components if I remove A? Now number of components is 4. Yes or no? Number of components is total 4. So what are the articulation points? Okay, A. This A is articulation point, because if I remove this A, then number of components will increase, will become 4. Right now you have 2, number of components will become 4. If I remove this, number of components is still 2. If I remove this, number of components is still 2. See, if I remove this, oh, sorry, 3 components. Oh, sorry. If I remove this A, if I remove this vertex A, now I have 3 components. Okay, so but the number of components is increasing. But if I remove this, now number of components is not increasing. If I remove this, number of components is not increasing. If I remove this, number of components not increasing. If I remove this, number of components not increasing, not increasing, not increasing. But if I remove this, now number of components will increase. How many? If I remove this, then how many components it will become? It will become total 5 components. If I remove this, now how many components we have? If I remove this vertex D, if I remove, how many components we have? Total 5 components we have. Okay, so finally I can say that vertex A, vertex D, these are the articulation points. So remember the definition. Definition is this. Please understand the definition. What is a cut vertex? What is the definition of a cut vertex? Cut vertex is basically a vertex. Let's assume your graph has k components. If your graph has k components, then cut vertex, okay, means what happens? If you remove this vertex, then number of components will increase. The number of components will increase. Like for example, here, if I remove this vertex, see this vertex, if I remove this vertex, number of components will increase. If I remove this vertex, number of components will increase. If I remove this vertex, number of components will not increase. If I remove this vertex, number of components will not increase. So this is not a cut vertex because number of components is not increasing. This is not a cut vertex. But remember, this is a cut vertex because number of components is increasing. This is a cut vertex because number of components is increasing. What about this? Is this cut vertex? Yes, this is cut vertex. If you remove this, number of components will increase. What about this vertex? What about this vertex? This vertex is not cut vertex. What about this vertex? This is also not cut vertex. Okay, this is cut vertex. Yes or no? This vertex is cut vertex. And this vertex is not cut vertex. Okay, so this is the definition. Just read the definition. Similarly, you can define cut edge. What is cut edge? Cut edge means an edge is cut edge if you remove it and the number of components increase. For example, please tell me, is this edge cut edge? This edge, is it cut edge? Yes, this is cut edge. Yes, this is cut edge because number of components will increase. If you remove this edge, number of components will increase. This is another component, this is another component. So number of components will increase. What about this edge? What about this edge? If I remove this edge, then this is not a cut edge. This is not a cut edge. What about this edge? What about this edge? Yes, this is a cut edge. See, very simple. If I remove this edge, then I will get 2 components. I will get 2 components. Similarly, if I remove this edge, then I will get 2 components, this component and this component. Okay, so the concept, so this is the concept, very simple. Cut vertex, cut edge means number of components should increase. Remember, number of components should increase. This number of components should increase. Let's see in this question. Okay, so tell me how many articulation points are there? So number of cut vertices. How many articulation points are there? Number of cut vertices. What is that? Number of cut vertices. See, this is not a cut vertex. This is not a cut vertex. This is an articulation point. This is not an articulation point. This is not an articulation point. This is articulation point. This is not articulation point. This is not articulation point. So number of cut vertices is 2. Okay, number of cut vertices is 2. Which are those vertices? Which are those vertices? I can say 2, 6. These 2 vertices. And how many cut edges? Number of cut edges. How many cut edges? Like this word, this edge is not cut edge. This edge is not cut edge. Not cut edge. Not cut edge. Okay, so there is no cut edge. In this graph, there is no cut edge. We don't have any cut edge. What about this graph? Cut edge is called bridge. Remember, this is another word for cut edge. Cut edge means bridge because it is like a bridge. if you understand cut edge is like a breeze. It is like a breeze. Okay, what it does, if this is your cut edge, like for example, let's assume this edge is your cut edge, then this is like a breeze. Some graph you have here, some graph you have here, okay, and some graph you have here. So this is the idea. So this is like a breeze between this and this part. Okay, this is the idea. So this is the idea of breeze. So you can notice this edge. If I remove this edge, then number of components will increase. So how many cut edges I have in this graph? Number of cut edges. Number of cut edges is only one. And what are the number of articulation points? Cut vertices. What is that? Number of cut vertices. That will be 2. That will be 2. Which are the cut vertices? The cut vertices are 2, 5. Cut vertices are 2, 5. These vertices are cut vertices. Now remember one thing. Okay, anyway, so this is another example. But before that, do you remember I told you in planar graph? Do you remember in planar graph I told you in a graph, 2 type of edges are there. In a graph, in any graph there are 2 type of edges. What are those? In any graph there are 2 type of edges. There are 2 type of edges. This I told you in the planar graph concept. Cycle edges and not cycle edges. Okay, so one is cycle edges. Cycle edges means which are part of some cycle. Okay, these are part of some cycle. Cycle edges means, okay, part of some cycle, part of some cycle, part of some cycle. And what is another? Another is non-cycle edges. Non-cycle edges, these are not part of any cycle. Okay, these edges, these are not part of any cycle. Not part of any cycle. So for example, you can notice that your cycle is like, if I give you a graph, A, B, C, D, E, F, G, H, I, K. Okay, so let's assume I give you this graph. So tell me in this, like, let's assume this is your graph, F, some, okay, P, Q. So these are your, this is a graph. Okay, in this graph, you tell me how many edges, okay, number of cycle edges, how many cycle edges we have, and how many non-cycle edges, or I can say number of non-cycle edges. You just tell me number of non-cycle edges. How many edges are not part of any cycle? How many edges? These are not part of any cycle. There is no, like, these are those edges which are part of some cycle, cycle edges. So remember, cycle edges are like this. If you understand cycle edge, then cycle edge is like this. Okay, like, let's assume this is a cycle edge. Then cycle edge is like this. It is part of some cycle. It is part of some cycle. Okay, so this is the idea of cycle edges. It is part of some cycle. And non-cycle edges, if you notice non-cycle edges, then non-cycle edges are basically like this. You have non-cycle edge. It is not part of any cycle. So there is some graph here and there is some graph here. So tell me one thing, which of them is a breeze? Which of these 2 type of edges, which is a breeze? Which is a breeze? See, cycle edges are part of some cycle. This is a cycle edge. This is part of some cycle. This is part of some cycle. Non-cycle edges, these are not part of any cycle. These are not part. There is, okay, these are not part of any cycle. So you can notice that non-cycle edges are your breeze. These are your breeze. Breezes. Non-cycle edges are basically breezes, or I can say cut edges. These are the cut edges. These are not cut edges. These are not breezes. Okay, these are not breezes. So this is the idea. So, okay, this is another definition of, I can say, cycle edges, because these are part of some cycle. For example, in this graph, this edge is part of some cycle. This edge is part of some cycle, at least one cycle. This edge is part of this cycle also, at least one cycle. This edge is part of some cycle. This edge is part of some cycle. this edge is part of some cycle, this edge is part of some cycle, this edge is part of some cycle, this edge is part of some cycle. So how many non-cycle edges? See, this edge is not part of any cycle. Okay, this edge, if you notice, so this edge is not part of any cycle. But remember, this edge is part of some cycle. This edge is part of cycle. So this edge is not part of any cycle. This is non-cycle edge. This is non-cycle edge. This is non-cycle edge. Okay. Anything else? Do we have anything else? No. So only 3 non-cycle edges we have. Is this clear? Only 3 non-cycle edges we have, because remember, these edges are part of this cycle. See, these edges are part of this cycle, and these edges are part of this cycle. This edge is part of this cycle, and this edge is part of this cycle. So how many are remaining? Only 2 edges. Only 3 edges are remaining. Okay, is this clear? So in this graph, how many? Tell me, what is the number of bridges? What is that? Number of bridges in this graph. So there are 3 bridges only. There are 3 bridges. See, if I remove this, the graph will disconnect. The graph will disconnect. If I remove this, graph will disconnect. If I remove this, number of components will increase. If I remove this, number of components will increase. But if I remove this, number of components will not increase. If I remove this, number of components will not increase. So number of bridges is 3. I hope this concept is clear. So there are 2 types of edges in a graph. This I told you in the planar graph. In any graph, whatever graph you take, there are only 2 types of edges. One is cycle edges, which are part of some cycle. Okay, which are part of some cycle, and non-cycle edges, which are not part of any cycle. Okay, like this is not part of any cycle. So finally, I can say that cycle edges are not bridges, and the non-cycle edges, these are the bridges. In this graph, you can notice that, okay, this is the original graph. If I remove vertex C, if I remove this vertex C, then number of components will increase. So this is a cut vertex. If I remove vertex B, number of components will increase. So this is a cut vertex. Okay, if I remove vertex E, then number of components will increase. So that is also a cut vertex. Bridge means cut edge. These things, these 3 things are same. Bridge is same as cut edge. Cut edge. And this is same as non-cycle edge. This is same as non-cycle edge. These 3 things are same. Okay. Bridge, cut edge, non-cycle edge. All these 3 things are same. Basically, all these 3 things are same. You have edge. This is not part of any cycle. This is not part of any cycle. This is not part of any cycle. Means this is your edge. Okay, this is bridge. Bridge means there is a city here, some city, there is some city here, and there is some city here. There is some graph here. So basically, this is your bridge. Can I say yes or no? This is a bridge. If you want to go from here to here, if you want to go, you have to go through this. You must go through this. So this is the idea of bridge, cut edge. Cut edge means these will removal. I can say in G, E is cut edge. E is cut edge. If and only if G minus E, number of components will increase in G minus E. So you have G. Okay, in this G, let's assume is cut edge. If and only if number of components will increase in G minus A. Okay, removal of A, I can say removal of E increases number of components. Increases okay, number of components. You know this. You already know this. Okay, so this is your graph. Now let's see in this graph. Tell me how many cut vertices. What is the number of cut vertices? How many articulation points you have in this graph? Number of cut vertices. Tell me. In this graph, how many vertices are cut vertices? See, this is not a cut vertex, but yes, this is a cut vertex. This is a cut vertex. So there are only 2 cut vertices. In this graph, there are only 2 cut vertices. And what are the cut edges? Number of cut edges. Number of cut edges means non-cycle edges. Non-cycle edges. This is non-cycle edge. This is non-cycle edge, only one. What about this graph? In this graph, how many number of cut vertices? What is the number of cut vertices? Cut vertices. So you cannot, this is not a cut vertex. Okay, this is a cut vertex. So B is a cut vertex. I can say that B is a cut vertex in this graph. In this graph, I can say that B is a cut vertex. Okay, the cut vertex. If you notice cut vertex, then B is a cut vertex. C is a cut vertex. D is not a cut vertex. E is a cut vertex. G is not a cut vertex. F is not a cut vertex. I is a cut vertex. So number of cut vertices is 4. Yes or no? Number of cut vertices is 4. And what about number of cut edges? What is the number of cut edges in this graph? In this graph, non-cycle edges. See, only these 3 edges are cycle edges. Notice. Only these 3 edges are cycle edges. Only these 3 edges. These are cycle edges. Only these are cycle edges. Apart from this, all these edges are actually non-cycle edges. 1, 2, 3, 4, 5, 6. Total 6 edges are non-cycle edges. You can notice this will increase number of components, increase number of components, increase number of components, increase number of components. And what about this graph? What about this graph? What is the number of cut vertices? What is the number of cut vertices in this graph? In this graph, C is a cut vertex. You can notice this vertex C is a cut vertex. So only one cut vertex you have. And okay, how many cut edges in this graph? What is the number of cut edges? Number of cut edges. Okay, so okay, there is no cut edge in this graph. There is no cut edge. So very simple. There is no cut edge. Okay, very simple. So this is the definition. Okay, just can you prove this? Try to prove this. Try this. Hi all. So let's see. So what is the definition of cut vertices? This is clear. A vertex in a connected graph. If you have a connected graph, then a vertex in connected graph is a cut vertex. If your graph becomes disconnected, a vertex is cut vertex if number of components will increase. Number of components should increase. Now let's see this thing. Let's see this thing. Okay, let G be a graph. You have G is a graph containing a bridge E incident with vertex V. Vertex V is cut vertex if and only if degree is greater than equal to 2. Please understand one thing. Please understand, okay, very important. This is very important. Okay, theorems related to, okay, very important. You can very easily solve all the theorems if you understand this. Very important. Okay. In questions related to, cut edges. In questions related to cut edges, what you have to think, like what memory picture you have to create. In questions related to cut edges, okay, the memory picture that you have to create, cut edges or cut vertices. Cut vertices. What memory picture you have to create? See, very simple. For cut edges, this memory picture you have to create. If the question is mentioning cut edges, cut edge means bridge, you know, okay. So then this memory picture you have to create. You know that bridge, or I can say non-cycle edge. Okay, these three things are same. I can say non-cycle edge. non-cycle edge. So basically this picture you have to create in your mind. In your mind, you have to create this picture. You have edge, some graph here and some graph here. Okay. This memory picture you have to create. Okay. This memory picture you have to create for cut edge. Means I can say there is edge and this area, this is separate area and this is separate area. Okay. This is separate area. This is separate area. There is no, okay. Can we have this type of situation? Please tell me. Can you have this type of situation? Can you have this type of situation? Can you have? Tell me, can you have this type of situation? No, you cannot have. No, you cannot have, because else this will become cycle edge. If I have this, if I have this, if I have this, then what will happen? If I have this, then this edge will become cycle edge. This edge will become cycle edge. So this will not happen. So this is the memory picture you have to create. This is a bridge. Okay, there is some part here, there is some area here, and there is some area here. Okay, so this is the picture that you have to create. Some area here, some area here. Very simple. And for cut vertex, what picture you have to create? For cut vertex or articulation point, this picture you have to create. Remember the Spider-Man picture. The Spider-Man picture you have to create. Okay, the Spider-Man picture you have to create. So okay, like okay, I can say that you can create this picture, this type of picture you can imagine. So okay, so there is some graph here, there is some graph here, and okay, there is some graph here, there is some graph here. But remember one thing. Tell me one thing. Is it possible that this and this are there is edge? Is it possible? Is it possible there is edge like this? Is it possible there is edge like this? Yes, it is possible. It is still possible, right? It is definitely possible. Okay. So actually, what picture you have to create? See, it is possible. Why it is possible? Because if there is edge, still this can be cut vertex. But actually, what picture you have to imagine? Let me tell you. You have to imagine that. Okay, like you have to imagine that there is no edge between these. Like basically, these are the separate parts. Are you getting my point? So okay, for example, if there is edge like this, then what picture you will imagine? If there is edge like this, then you can imagine this picture. You can simply imagine this picture. You can merge them. Yes or no? Did you get it? You can merge them. If you have this type of situation, then you can merge them. You can merge them into one. Similarly, if you have this type of situation, then you can merge all these three things. You can merge all these three things. And is it possible? Please tell me, is it possible now? It is possible. It is not possible. Okay, this is not possible. So anyway, what I am saying that you have to imagine this picture. You have to imagine, and imagine there is no edge here. Imagine there is no edge here. And imagine there is no edge here. Because if there is edge, then you will merge. These two you can merge. So these two you can merge. So this is the picture. This is the memory picture for cut edge, and this is the memory picture for cut vertex. Please tell me, this is clear? Yes or no? So very simple. The definition is very simple. Okay, this is your bridge. I can say this is your cut edge. If you understand this memory picture, you can solve any question. Whatever question you want, you can solve any question. Okay, this is your cut edge. This is the cut edge. Some graph here, some graph here. Tell me, for a cut edge, can you have like, okay, some graph here, some graph here. Can you have something more? Can you have something more? Like, can you have something more? No, you cannot. No, you cannot, because this is only, okay, this is the only situation that can happen. But for a cut vertex, this type of situation can happen, that there is some graph here, there is some graph here, there is some graph here, and so on. Okay, there is some graph. Okay, just assume that there is no edge here. There is no edge here. Because if there is edge, then you will merge. Them. Okay, anyway. So this is the memory picture. Let's see this question now. Now this question is very easy. You have a graph in which you have bridge. In a graph you have bridge. So if you have a bridge, just think about it. If your this edge is a bridge, this edge is a bridge, u comma b. Okay, this edge is a bridge. Tell me one thing, there is some graph here, there is some, you know that there is some graph here, and there is some graph here, and there is some graph here. You tell me one thing. Okay, you tell me one thing. When, tell me one thing. When can you say that, okay, so this is your bridge. Then in this situation, tell me, when can you say that this V is cut vertex? When can you say that this V is cut vertex? This V is cut vertex. When can you say? If this is cut vertex, it means number of components should increase. If it is cut vertex, number of components should increase. Number of components should increase. Okay, so you can notice if V is cut vertex, if and only if its degree is greater than or equal to 2. If and only if its degree is greater than or equal to 2. Because remember, if its degree is 1, just think about it. Very simple. Let's take this graph. Let's take this graph. You have a vertex V and you have vertex U, and let's assume you have vertex A, you have vertex B. Let's assume this type of graph you have. Now you can notice this is your bridge. This edge is a bridge. Okay, so tell me, can I say this V is cut vertex? Is this V cut vertex? This is not cut vertex. This V is not cut vertex, because if I remove this V, then number of components will not increase. But you can notice that this U is cut this is cut vertex. This is cut vertex. Okay, so you can notice that, okay, this vertex will be cut vertex if and only if its degree is greater than or equal to 2. Here this has degree 1. Here degree this is 1. And here degree of this vertex, that is greater than or equal to 2. Is this clear to everyone? So very simple. If you have a bridge, then these vertices will be cut vertices if and only if you have degree greater than or equal to 2. If your degree is greater than or equal to 2, then these will be the cut vertices. To how many people this is clear? Please let me know. Is this clear to everyone? Tell me one more thing. In this graph, let me give you a K2. In this graph, how many cut vertices? In this graph, what is the number of cut vertices? There is no cut vertex. And what is the number of cut edges? There is one cut edge. Let's see the next thing. Okay, so these are the observation. If you remove one vertex, then what can happen? Tell me from any graph. Okay, this is one. Okay, observation 1, note number 1. So tell me, from any graph, okay, whatever graph you have, any graph G, then tell me G minus V, what can you say about this? Okay, any graph G you have with number of components equal to K. Number of components equal to K. Then if you remove one vertex, then what can you say about number of components? Okay, you have any graph G you have, remove one vertex. Basically, you get a new graph G dash. This is G minus remove one vertex. You are removing one vertex V. So what can you say about number of components in G minus V? Number of components in G minus V. Let's assume that is M. So what that will be? What can you say about the range? See, the number of components can decrease only by 1. The number of components can decrease, right? When it will decrease? When this will happen? Tell me when this will happen. Number of components will decrease. When this will happen? When you have isolated vertex. Okay. Abhipsa, we are removing vertex. Why are you adding A's? Why are you adding A's? Vani, why are you adding A's? I am removing vertex. My question is, you have any graph G, any graph G you take, any graph G you take, in which number of components is K, you remove one vertex, you remove one vertex, then what can you say about number of components? What can you say about number of components? Like for example, let's consider this graph A, B, C, D, E, F, G, H, I, K. Consider this graph. In this graph, all your answers are there. Tell me one thing. In this graph, how many components? What is the number of components? Tell me number of components. Number of components K equal to number of components, that is total 3. Total 3 components you have. Now, if I remove from this G, if I remove H, then what will be the number of components? From this graph, if I remove this H, then what will be number of components? Now the number of components will be 2. If I remove this A, then what will be number of components? If I remove this A, then 3, 4, 5, 6. Total 6 components. If I remove this B, then how many components? Number of components. If I remove this vertex B, then there will be 4 components. And if I remove this vertex G, then number of components will be same. Then number of components will be same. Yes or no? Is this clear? Anyone has any doubt in this? So did you understand that when if you remove one vertex, then number of components can decrease only if you have isolated vertex. Because of isolated vertex, if you remove this isolated vertex, then number of components can decrease. Else number of components will not decrease. If you remove isolated vertex, then number of components will decrease. If you remove this, then it will decrease by 1. Then the number of components can decrease by 1. But okay, tell me, what is the maximum number of components you can get? One vertex if you remove, then what is the maximum number of components you can get? That is number of vertices minus 1. That is n minus 1, number of vertices minus 1. So you have a graph G in which you have number of vertices. Let's assume number of vertices is n. So you can notice, because for example, consider this graph. Consider this graph G. A, B, C, D, E. Consider this graph G. In this graph G, number of components is equal to 1. This is the number of components. If I remove A, if I remove this vertex A, then what will be number of components? Number of components, that will become total how many? That will become 4. If I remove B, number of components will still remain 1. Okay. If I remove C, number of components will remain 1. So you can notice that number of this is your nothing but n minus 1. So in worst case, okay, when you remove one vertex, then in worst case, okay, these many components you can get. Like every vertex will become isolated. Okay, every vertex can become isolated. Every vertex, like if I remove this, every vertex will become isolated. Okay, and similarly, it can decrease also, but it can decrease by only 1. If I remove this, then it can decrease by 1. If I remove an isolated vertex, then it can decrease by 1. Okay, remove isolated vertex. To how many people is this clear? This not 1. This is your GATE exam question if you remember. This is a GATE exam question already. We have already seen this question. GATE exam question. In the same question, if they tell you that there is a graph without isolated vertices, let's assume they tell you that there is a graph without isolated vertices. Let's assume this question is given to you. Okay, they say that question is graph without isolated vertices. Graph without isolated vertices, or I can say graph with, okay, they can ask you like this: graph with minimum degree 1. Graph with minimum degree 1. Okay, so you have a graph G with minimum degree 1. It means there is no isolated vertex. In this situation, what will happen? The number of components cannot decrease. See, if you remove one vertex, number of components cannot decrease, but it can increase. But it can increase, yes or no? So it will become from k to n minus 1. Because now it cannot decrease. Now you cannot decrease. If I remove one vertex, okay, remove one vertex for removal of one vertex. Is this clear? All these questions. So they can ask you anything. So you should understand all these concepts. Isolated vertex has degree 1. Nikhil. Nikhil, if minimum degree is 1, it means no isolated vertex. This means no isolated vertex. Minimum degree 1. Minimum degree is 1. What it means? Please tell me. What it means? It means there is no isolated vertex. You don't have any isolated vertex. It simply means there is no isolated vertex. So what is the problem? Array, see this graph. See this graph. In this graph, minimum degree is 1. Nikhil, in this graph, minimum degree is 1. Look at this graph. Minimum degree is 1. But still, if you remove A, number of components okay, maximum number of components you can get is n minus 1. Is this clear? Please let me know if you have doubt. Okay, let's move on now. So this is the idea. And tell me one more. If you remove one A's from any graph, this is your note number 2. From any graph, you have any graph you have, and from that graph, if you remove one A's, any graph G you have, in which number of components is K. Let's assume number of components is K. If you remove one A's, you are removing one A's. This is what you are doing. You are removing one A's. You are removing one A's. Remove one A's. Okay, remove one A's. Then tell me, what can you say about number of components? What can you say about number of components in G minus E? What can you say about that? Number of components in G minus E. What can you say about this? If you remove one A's, then what will happen? If you remove one A's, you are removing one A's. Then number of components can only increase by 1, remember. Okay, the number of components can only increase by 1. Can only increase by 1. Number of components either can become K plus 1. See, the number of components, this will become either K plus 1 or K, or it will remain as it is. Okay, either K or K plus 1. Only this can happen. Why? What is the reason? Because you know the A's that you are removing. Just think about it. If you are removing cycle A's, okay, if you remove cycle A's, then what will happen? If you remove cycle A's, you are removing one A's, which is cycle A's. Then what will happen? And if you remove non-cycle A's, then what will happen? So if you remove cycle A's, then what will happen? You are removing a cycle A's. Then number of components will remain same. Number of components remains same. Remains unchanged. Number of components will not change. If you remove a cycle A's, you are removing a cycle A's, then number of components will unchanged. And if you remove non-cycle A's, like, okay, this type of A's you are removing. You are removing this type of A's, non-cycle A's. If you remove this type of A's, then what will happen? This A's you are removing, then number of components can increase by 1. Okay, so in this situation, number of components will increase by 1. Okay, increase by 1. Increase by exactly 1. So please tell me, did you understand this? So note number 2. If you remove one A's, then number of components can increase. Okay, either it will remain the same. If you remove cycle A's, okay, then number of components will will remain unchanged. And if you remove non-cycle edge, this type of edge, if you remove, if I remove this edge, if I remove this edge I am removing, then number of components will increase by exactly 1. So these are the observations you can notice. Removal of a vertex, removal of any vertex may increase the number of components by at least 1. Okay, but it can decrease also. If you remove a isolated vertex, then it can decrease also. But if you remove one edge, then how much increase can happen? At most 1 increase can happen. But if you remove one vertex, how much increase can happen? The number of increase can happen is at least 1. Similarly, and vertex of cut edge. Okay, when can I say they will be cut vertices? And vertices of cut edge. When can I say there will be cut vertices? If their degree is more than 1. This we have seen. This we have already seen. Your edge, this is your cut edge. Okay, this is your cut edge. Now you have this vertex V, this vertex U. Okay, this is your graph. Now you can notice that this will be cut vertex if and only if this will be cut vertex if and only if its degree is greater than equal to 2. Very simple. And you can notice every non-pendant vertex of a tree is a cut vertex. Can I say every non-pendant vertex of a tree? You have a tree. In a tree, okay, so yes, every non-pendant vertex of a tree is a cut vertex. Very simple. Next, tell me one thing. So anyway, these are the definitions of cut edge. Remember cut edge definition. They can give you either they can say directly. Remember, these following statements are equivalent. All these 3 statements are equivalent. These are the definitions of cut edge. So either I can directly say that E is cut edge, either I can directly say, or what I can say that E is not a cycle edge. I can say yes. So these 2 things are same. E is a cut edge, or I can say E is not a cycle edge. There is another way. What is another way? Tell me one thing. When can I say that this is a bridge? When can I say this is a bridge? This will be bridge if and only if there are at least 2 vertices. There are at least 2 vertices. Okay. There are at least 2 vertices such that every path from U to V goes through E. Every path. There are at least 2 vertices such that every path goes through E. Yes or no? Every path goes through E. Okay, whatever path you take from U to V, okay, whatever path you take, okay, I can say that every UV path goes through V. Every UV path goes through E. Okay, I can say, or I can say every UV path contains E. Okay, every UV path contains E. Now remember one more thing. In this same, if I have a cycle edge, okay, like let's assume that if I tell you that you have vertex V, U comma V, assume, okay, this is my question. Your vertex U comma V, your vertex U comma V, and let's assume that I tell you that every path, okay, this is what I tell you. I tell you that every path UV, okay, this every path UV, okay, contains E, contains edge E, contains edge E. Then what can you say about E? Okay, what can you say about E? What is E? What can we say about E? Just think about it. Please think about it. Your vertex U. Okay, you have vertex U. This is your vertex U. This is your vertex V. And what we are saying? We are saying that, okay, every path, if you take every path that will go through, that will contain E. Every path will contain E. Every path will contain E. Every path will contain E. What it means? It means that if you want to go from U to E, if you want to go from U to V, then you have to go like this. You have to go like this. You cannot go like this. You cannot go like this. You cannot go like this. What it means? It means this is not part of any cycle. See, you cannot go like this. You cannot go like this. Remember, you cannot go like this. It simply means what? It simply means that this E, I can say this E, this cannot be part of any cycle. This E cannot be. And remember, can you go like this? For example, please tell me, can you go like this? Like, okay, can you go like this? Because the question is saying that every path contains E. The question is saying every path contains E. Every path contains E. So you cannot go like this. So finally, I can say that this E, finally, I can say this E is what? This is non-cycle age. Finally, I can say this is a non-cycle age, or I can say cut age. Did you understand? It will be a cut age. It will be a cut age. Cannot, okay, it definitely will be a cut age. If every path, please understand this word, every path. Understand this word. If every UV path contains E, if every UV path contains E, if it contains E, then this E will be a cut age. Okay, so basically E is definitely a cut age. Tell me, is this clear? Let me know. So all these three are definitions, you can notice. Okay, let's see what should be the answer for this question. Think about it. Hi everyone. Yes. So what will happen here? Tell me one thing. If I make this question like, okay, if I remove, see, this is the question. If every edge is a cut edge, okay, if every edge is in a connected graph, every edge is cut edge. Okay, the graph is connected. The graph is connected and every edge is a cut edge. Then what can you say about the graph? Then what is this graph? Then what is this graph? Tell me. The answer is very simple. The graph is simply tree. The graph is simply tree. Every edge is cut edge. What it means? Every edge is cut edge. Every edge is a cut edge. Cut edge means non-cycle edge. Every edge is non-cycle edge. Every edge is non-cycle edge. It means what? Every edge is non-cycle edge. It means what? There is no cycle in the graph. It simply means there is no cycle in the graph. There is no cycle in the graph. So your graph is acyclic. So your graph is definitely acyclic. Your graph is acyclic because remember, every edge is cut edge. Every edge is cut edge. Okay, if every edge is cut edge, then I can say that no cycle in the graph. So your graph is acyclic and it is given connected. It is given connected also. Okay, it is given connected also. Also, it is given that it is connected. Given connected. So these things. So okay, acyclic and connected, acyclic and connected. That simply means tree. Simply means tree. Yes or no? So what can you say about this graph? This will be a tree. This will be your answer. This type of question, see, GATE exam is all about this type of questions. They can ask you any question, they can ask you. This is a very simple question. Every age is a cut age. Every age. Whatever age you take, that is a cut age. Cut age means non-cycle age. Cut age simply means non-cycle age. It simply means that there is no cycle in your graph. It means your graph is acyclic. And it is given that your graph is connected also. So finally, connected acyclic, that means tree. In the same question, if I remove this connected, in the same question, if I remove this connected, now what will be the answer? Then what is this answer? Then now this will become a forest. Now the answer will be forest. This answer is wrong. This answer is wrong. This will be a forest. Okay, so this is your this is the idea. So you can notice that every age. Okay, if you okay, so this is the theorem you can make. I can say that okay, in G, okay, G is a tree. If and only if G is a tree, or I can say sorry, I can say G is a forest if and only if every age is cut age. Yes or no? If and only if every age is cut age. Means if you have forest, means it means if you have forest, so forest implies every age cut age. Forest implies every age cut age. Okay, and every age cut age, that implies forest. So this is the idea. A cut age in a and if your graph is connected also, if it is connected also, then okay, a cut age. Anyway, this is the definition of cut age. So you can notice that in a connected graph, if every edge is cut edge, then your graph is a tree. So you can notice if every edge is cut edge, then it means there is no cycle in the graph, and your graph is connected also, so it must be a tree. Did you understand? So far, anyone has any doubt? Let me know. Do you have any doubt right now at this moment? Do you have any doubt? Please tell me. Any doubt, anyone? Did you understand all these concepts? Very simple. Manideep is asking, if cut edge is removed, also the vertices are removed. Is it happens? If you remove edge, will you remove vertex also? We never do that. We have already seen this in the previous classes. If you remove edge, you have this graph A, B, C, D. Okay, you have this graph. If I remove this edge, okay, let's remove this edge. Let's call this way is 1, 2, 3, 4. Let's call this. Okay, from this graph, let's remove edge edge 1. G minus 1. What I will get? G minus 1. I will get this. This graph I will get. So this is the G minus 1. And what is G minus 2? What is G minus 2? G minus 2 will be this. This is G minus 2. Okay. What is G minus B? What is G minus vertex B? I am removing vertex B. This vertex B I am removing. Now my graph will be like this. Now this will be my graph. Okay. So here you are removing edge. Here you are removing vertex. If I remove this vertex, now these edges are gone. If I remove this vertex, this I will get. If I remove this vertex, this is what I will get. If I remove this vertex, this is what I will get. If I remove A, this is what I will get. If I remove 2, this is what I will get. If I remove 1, this is what I will get. If I remove 4, this is what I will get. Okay. So let's see this question. Can you prove it? Very simple question. Very simple. So can you prove it? If your graph is connected, order 3 or more. Order means number of vertices. So number of vertices is greater than 3 or more. If G contains a bridge, then G contains a cut vertex. If G contains a bridge, then definitely G contains a cut vertex. Can we do this? Remember, G contains a bridge. So already you have a bridge. Let's assume your bridge is E. So you have a bridge. Your graph G, it has a bridge. It has a bridge. Okay. If it has a bridge, it means there is some part here, there is some part here. And what this question is saying, this is connected. The graph is connected. That is fine. Very good. Next, number of vertices is greater than or equal to 3. So tell me one thing. Please tell me one thing. This graph is connected. This graph is connected. Okay. And this is your edge E. This is your edge E. Now the question is saying that G contains a cut vertex also. Can I guarantee that G contains a cut vertex also? Can I guarantee? Can I guarantee that G contains a cut vertex also? Can I guarantee G contains a cut vertex also? Yes, because it is given that number of vertices is greater than or equal to 3. This is given. Number of vertices is greater than or equal to 3 and the graph is connected. These things are given. The graph is connected. Number of vertices is greater than or equal to 3. So this is your vertex. This is your vertex. Where is that extra vertex? You have at least 3 vertices. You have, where is that extra vertex? Either here or here. Where is that extra vertex? Either side. Very good. Very good. Either here or here. Where is that extra vertex? That extra vertex is either here or here. And this graph is connected. This graph is connected means there is a path. Now you can notice. Now you can notice this A will be what? This A will be cut vertex. Because this A has now degree greater than or equal to 2. This A has degree greater than or equal to 2. This A. So this A is cut vertex. Please tell me, is this clear? All these questions, they have the same template. The same template we have. Please tell me, is this clear? The template is same. Number of vertices is 3 or more and the graph is connected. The graph is connected, number of vertices is 3 or more. So this vertex A, this will have degree greater than or equal to 2. So it is a cut vertex. You can note this is a cut vertex now. Okay. Let's see this. Let's see this question. All these are questions. All these are standard questions. Some of them have come in the GATE exam. Some of these questions have come in the GATE exam. So tell me, all these are standard questions. A vertex in a connected graph is a cut vertex if and only if. A vertex is a cut vertex if and only if there exist 2 vertices distinct from this, such that there is at least one UW path in G and V lies on every path. This is actually true. Because remember, your vertex is cut vertex, your graph is connected. These are the things. Your graph is connected. Your graph is connected. And okay, let's assume this vertex A. Let's assume this is a cut vertex. What is the picture? I told you memory picture for cut vertex. Please tell me what is the memory picture. The memory picture for cut vertex is Spider-Man. The memory picture for cut vertex is Spider-Man. Memory picture for cut vertex, that is Spider-Man. That is Spider-Man. Now you can notice that. Okay, so if this and graph is connected and the graph is connected, the graph is connected. It means what? And this is a cut vertex. This is a cut vertex. It simply means what? It simply means that there is this vertex, there is this vertex, and you can notice every path will contain A. Every path must contain A. Every path must contain A. At least 2 vertices you must have. You must have at least 2 vertices you must have. Okay. In worst case, this can happen. I told you in the memory picture. I told you in the memory picture, in worst case, this can happen. This can happen. In best case, this will happen. In best case, this will happen. But in worst case, this can happen. Now you can notice that this vertex and this vertex, every path will contain A. Every path will contain A. You cannot have like this. You cannot have like this. I told you. Do you remember from the memory picture? You cannot have like this. Because if you have like this, if you have like this, now this is not a cut vertex. This is not a cut vertex. Okay. Is this clear to everyone? This question. So just Spider-Man, this is the idea. Okay, so you can notice that like this, you can understand. If you want, you can understand like this, very simple. Okay, so now let's take a break. And what I will do after the break, we will continue, but I will create a new session. So the break will be little bit long. Okay, we will create a new session. So new session I will create on the website. New live session we will create. Okay, you can take a break, like 15 minutes break you can take. Okay, so yes, in the evening also we have a class today. Okay, basically I want to complete this topic. Okay, after the break we will complete this topic, like what is connectedness, what is vertex cut, all these what is connecting this connectivity number. These topics we will study. This is the last question slide, Yuvraj. So we will create a new session, okay, at 9:45. New session we will create. So you have to join by the website. So this session I will terminate. Okay, you can join the next session after 15 minutes. Okay.